All right, today we're going to take a look at section 1.9, which is scientific notation. Warning, I may teach this a little bit different than you've seen it before. I learned it probably something like what you did, but I think there's an easier way to explain it, and so that's the way I tend to go. If you feel like you understand scientific notation in a different way and you're getting the same answers as me, fabulous, go with it, okay? So we'll start with the basic form. So the basic form for scientific notation. All right, so the condition on the values, oh, there's a typo on this. A times 10 to the n is that the A value is between 1 and 10. It could actually equal 1. I mean, like it's less than or equal to the number 1. But it is strictly less than 10. So we're not dealing with two-digit numbers for A, right? It's going to be a one-digit number. It could have decimal places, but only one in the units digits. The n value is an integer. And if you'll remember, integers are positive and negative whole numbers. So it could be -7, it could be 52, it could actually be 0. It'd be weird, but it could technically be a 0. So we're going to talk about how we move in and out of scientific notation. So first we're going to talk about how we move into scientific notation. So if we have standard notation, just a number that you were given, and you want to put it in scientific notation, you'll move the decimal point to create a value between 1 and 10. You'll count the
number 8, right?
Yes, it is homework number 8 we just submitted. Okay, you'll count the number of moves that you made, right? How many locations that decimal point changed position. If you actually have a large number to start with, your exponent's positive. If you have a small number to start with, your exponent's negative. And I've clarified for you what I mean by small and by large, because those are relative like phrases. But large means larger than 10, and small means smaller than 1. Okay, it's all based on those numbers 10 and 1. So this sort of description of positive and negative exponents is the part where I teach it a little bit differently than you might have heard it before. So undoubtedly we need some examples of this happening. So our first example is 298,000. So I'm going to ask you the same question that I've been asking my 6th graders this summer when we have been talking about where's the decimal place. There's not a decimal in this number, but where is the decimal place? Yeah. It's after the 0 at the very end, okay? So even if you don't see it, it's there. And I need it to be where? Right, it needs to be between the 2 and the 9 because I'm supposed to be creating a value between 1 and 10. So there's nowhere else I can put it that will do that. And I need to count how many places it moves to get from the end to where the red dot is right now. So this is 1, 2, 3, 4, and 5. Everybody good so far? Okay, so what that means is I've got the number 2.98 times 10, and it's to the power 5, and I need to still decide, is it a positive 5 or a negative 5? Positive. Why? Because it's a big number. It's bigger than 10. It's positive because it's a big number. Okay? And then you're done. Okay. Next one, we see the decimal in this one. Where does the decimal need to move to? Yep, between the 3 and the 8, and we will count 1, 2, 3, and 4. So I have 3.8. Yep, and why is it negative, Maxwell?
Because it turns into a decimal point.
Yeah, it was a small number to begin with, right? The number itself to begin with was small. So my exponent needs to be negative. Negative exponents represent, in scientific notation, they represent small numbers. And positive exponents represent big numbers. Yeah, it's a chemistry thing too, you bet. Absolutely. Okay, very good. Lovely. The other one that we're going to do is to go the other direction. So this is going from scientific notation into standard notation. Again, we're going to move the decimal point. We're going to move it the number of values or places that the exponent tells you. So if the exponent's a 7, you move it 7 places. If the exponent's a 2, you move it 2 places. If the exponent's positive, the number will get larger. Positive exponent, big number. If the exponent is negative, the number gets smaller. Negative exponent, small number. So the reason that I talk about my exponents in positive and negative and large and small is because I can say it the exact same way no matter whether I'm moving into scientific notation or out of scientific notation. And if you talk about moving decimals left and right, you have to change what you're saying in order to talk about whether you're moving into or out of scientific notation. So this way, it always says the same thing. Positive, larger, negative, smaller. So that's why I do that. So let's actually do some examples. So we have one that's 3.2, and it's times 10 to the negative fifth. So what does that negative 5 exponent tell me to do? It tells me two things. Okay, so I'm going to move it a specific direction, and it's going to make it smaller. So in this case, it's actually going to move it to the left, okay? And then it also tells me what? How many places to move it. So it's 5. So right now my number is 3.2, and I need to make the number smaller. So I'm going to put the zeros before my 3.2, and I can count it over. 1, 2, 3, 4, and 5. So this is the correct location. So you can write the 0 at the beginning before the decimal place, or you can leave it off. It really doesn't matter. Then you're going to have 4 zeros and a 3.2. Okay, it's probably a good idea to check at the end and make sure. I've got a small number here. Did I have a negative exponent? I did. So I definitely moved it the right direction. And I can check to see by counting again if I wished to make sure that I moved it 5 places. Number 4, 6.24 times 10 to the third. What is that exponent telling me to do? Two things. Make it bigger and move it 3 places, right? So in order to move it and make it bigger, I have to move it to the right. Okay? So I'm going to move it 3 places. Here's 1, 2, and 3. So I didn't need my extra zeros I added. I usually just add a bunch to start with. So I end up with the number 6,240. Okay, is that good? All right. The last thing we're going to do in this section is to talk about how we write or how we calculate things when we have scientific notation problems given. So these are all problems that are given in scientific notation to start with, and then we're doing some sort of operation, multiplying or dividing in particular. So it says calculate the following, and then it says write your answer in scientific notation. So the placement of this section, section 9, right, is happening because we've already talked about exponents, and we're going to be using exponents in our discussion here. So we're going to actually do some of these properties of commuting, which means moving things around, and associative property, regrouping, in order to work these. So in particular, I'm going to talk about multiplying the 8 and the 6, right? Those are the whole number parts, or the parts that are not in scientific exponent form anyway. And then I have the 10 to the 12th, and I have to the 10 to the 15th. Okay, so I'm regrouping them, and I'm allowed to do that because it's all multiplication, and that's the commutative and associative property at play. So if I do that, what is 8 times 6? 48. Okay? Now that is not scientific notation yet. We will have to do an extra step here in a moment to fix this issue. But keep going for the moment. The next thing I have is I have 10 to the 12th and 10 to the 15th. So what do I have to do based on your properties of exponents in our last section? Yeah, I add them. So this is times 10 to the 27. Right? 12 and 15, yeah. Okay, if you leave it right here, you've stopped short. Because 48 is not between 1 and 10, right? What I need is I need the decimal point to be here, yeah? Yeah, that's what I need. And so we do need to change it to 4.8, but obviously I can't just change 48 to 4.8 and not change something else too, right? So, is 48 a big number or is it a small number? It's a big number. It's a big number, so what I do to compensate is I make my exponent 1 bigger because I moved it 1 place. Big number, bigger exponent.
So, if it was, a smaller number, would you just take one away from?
Yes, you would. And I think that's our next example.
Okay.
I think. I could be wrong. No, our next number is going to be big. I may not have an example of a smaller one. But yes, let's say, for instance, that at the very end, because that's a good question, Haley, usually I try to get a variety of answers showing up at the end. Let's say at the end you ended up, after you did your multiplication, with a number that's like 0.25, whatever, and it was times 10 to the fifth. Then yes, you would change the location here to 2.5, and then you would take one away because the number was smaller. Yes, that is what you would do. All right, so let me just set this up here because it's a side. Okay, we're going to do the same thing here. We've got 1.2, and we have 9.5, and we have the 10 to the negative 2, and we have the 10 to the 12th. You'll notice that I wrote this with parentheses around everything. Last time I wrote it with dots between. It originally starts with the multiplication x's between. It doesn't make any difference how you write the notation. It's all the same. But the process works the same way at the end too, right? So I need 1.2 times 9.5. Feel free to grab a calculator. What do you get? 11.4 is correct. Times, okay, so what is 10 to the negative 2 and 10 to the 12? 10 to the 10, yes. Yeah, okay, I have it written down right. Okay, but I don't want 11.4. What do I need to do? Yeah, I need to move it between the two ones. So it should be 1.14. And what will happen to my exponent? It'll get one bigger. Yeah, because the number was bigger than 10 to start with. So my exponent gets one bigger. Okay, it's always what the number was to start with that I consider whether or not was the number big or small. Because the number to end with is always between 1 and 10. And I can't make a justification anymore. Yes?
So when you were saying like that the original number was bigger than, was larger, whatever.
Yep.
Right, were you looking at the 9.5?
Nope, I'm looking at the 11.4. And I'm looking at the 48. I'm looking at the answer that's not quite in scientific notation yet.
Okay.
Yes. Good question. Okay, so this is what we do when we've got multiplication. Make sense? Don't stop one step short. Make sure you finish it through to the end. Let's take a look at what happens when we have division. So the division works just the same way in the sense that I sort of pair the values up that go together, right? The 8 and the 2, they go together because they don't have exponents. And these powers of 10, they go together because they do have exponents. Same base with exponents. So what do I get when I do 8 divided by 2? 4. Now, the division wouldn't necessarily have to be so beautiful. This one's very nice. It's very, very, very even, right? It doesn't have to be quite that nice. The 10 to the 4th and the 10 to the negative 6th. What do we do with those exponents? We subtract them, and be very careful because you're actually subtracting a negative. So it's 4 minus negative 6. Yeah, so we end up with positive 10. So the thing to be careful of here too, or another, not be careful of, but another way to do it is you also could just move the 10 to the 6th in the numerator. Some of you probably did that on your last section where you just shifted things around. And if you moved the 10 to the 6th up, because now it's positive, you would add the exponents together. And 4 plus 6 is also 10. So either of those perspectives are going to give you 10 to the 10th. So we have 4 times 10 to the 10th. Okay, any questions on that? Okay, last example for today. 9 times 10 to the 8th divided by 2 times 10 to the 3rd. What would I do first? All right, 9 divided by 2, which is what? It's 4.5. The number doesn't necessarily have to give you something, by the way, that's between 1 and 10. If it didn't, we'd be doing the same thing we did over here on 5 and 6. Okay? We'd be moving it around and adding or subtracting a number. But that one did. It gave me a 4.5. And then what will I do with those exponents? Subtract. Okay? So since it's division is always subtraction, they both happen to be positive here, so that's kind of nicer. 8 minus 3 is 5. And again, I could end up with a negative exponent, right? If I had had the 10 to the third over the 10 to the 8th, I would have done 3 minus 8, and I would have had a negative 5 as my exponent. Perfectly reasonable. So this is what I end up with instead, or in this one.
So is it okay to have a negative exponent?
Absolutely okay to have a negative exponent in scientific notation. That's a really good question because in our last section, we always wanted the answer to have a positive exponent when we're done. But in this section, our goal at the end is to always have it into this form, which means that negative exponents on the power of 10 are perfectly acceptable. It is worth noting again, since I switched my screen back here, that that exponent is still always a whole number. Positive or negative, right? But I'm not going to have a decimal or a fraction or anything like that. That won't happen when I'm working in scientific notation. Okay, any questions? All right.